And anyway, so, and there are two kinds of motivations I want to tell you. So one motivation is that we can ask in general, what ways do we know of achieving capacity? So if I'm still in coding and I'm interested in achieving a code that gets close to the optimum limits. And so when I gave you the overview, I didn't particularly emphasize this, but we have already mentioned this. The first one that we haven't talked so far was we can look for codes with good weight distribution. So this is a sufficient condition, and when I mean good, I mean close to random. So if I pick the code randomly, everything is binary here, and I pick a code of rate R, then it's a nice exercise to compute what the weight distribution is. And so if this is the relative weight from 0 to, so this is the relative weight omega from 0 to 1. And this is 1 over n, the log of A of omega, where A of omega is the number of words of weight, of relative weight omega, and I take the 1 over n log, so that's the exponent, then, and I do this for a particular rate, then this exponent will look like R minus 1 plus H2 of omega, where this is the binary entropy function. So it means if you, so this is a half here, so most code words in the code will be, so if you randomly just pick with uniform distribution from all the words of length, binary words of length n, 2 to the n are code words, and you're looking at the expected number of code words that you get for particular weights, then you will see this. So roughly, so essentially all the code words that you pick will be of weight a half. Okay, so there will be already, this is the exponent, there will be already 2 to the nr of those. And then there will be exponentially less on the side, okay, and then essentially there will be something where this hits 0, so you'll be very unlikely to see something less than that distance, okay? And this is symmetric around 0. And so this, it's just a nice computation to see how you get that. And when you then try to write down a proof, and it's just a few lines to see, for example, for the binary ratio channel, why for such a code, indeed you get capacity, you will see that it's actually not crucial that you have words like this, but there will be one critical thing, and that's called the Elias distance. So there will be one particular weight, and for the erasure channel, the critical one is epsilon over 2. So for example, if you do an erasure channel of erasure probability half, then the Elias distance will be a quarter. And so it will tell you that as long as you don't have, so if you write down the bound, as long as you don't have more code words particular around this critical distance, then you'll be doing fine. And then you have a little bit of slack around, around here. So you could have a little bit, you could deviate a little bit from this critical one around the other points. And so one proof then is to simply say that any code that has a weight distribution that doesn't deviate too much, and I don't tell you exactly what that means, from that weight distribution will achieve capacity. Okay, so in particular, it can deviate quite a lot here and doesn't have to produce 0, could even go down here and you can compute this. Okay, so that's one way. You find a code that has a very good weight distribution. That's, of course, under optimum decoding. There's no complexity that goes in here, right? Okay, then we have seen that we can, we have not talked about it, but some of you have already heard lectures, polar codes, right? So that's a completely different way, just this based on the chain rule of mutual information. And again, that's a way to get a capacity achieving code. Now these codes, if you have code like this will be universal. So a code like this will be universal but in general not efficient. So meaning there's no, in general, there will be no efficient algorithms to do either the encoding or the decoding, right? And it will be in general non-constructive, right? In general, I mean, maybe it is constructive, but at least these random codes in general are not constructive, right? So perhaps you can get a particular structure that will do it. So here, these are constructive. That's very nice. So there's no randomness. You don't need to de-randomize it. They are, unfortunately, non-universal. So this depends on the channel. But you know, they're efficient in the sense that you have efficient encoding and decoding algorithms, and these are something like n log n complexity. Yeah, so because you know, there's really only when you compute the bound, you will see that there's really one critical distance at which, and this depends on the channel. So for the BSC, that's the Elias distance is this. For the BSC, it's a different distance. So you know, you probably, depending where you are, there are different critical distances. You know, sorry, whatever channel you are, you probably can find for any distance, you can probably find a channel for which this is the critical distance somewhere. But if you're not interested in some, you know, in some kind of channel and you want to transmit over that, there might be many, you know, it doesn't have to be a random one. As long as you guarantee that it's close enough to that, you will achieve capacity. Is that what you ask? Okay, so, yes?
Can you elaborate on what you mean by universal here?
So these, yeah, if you pick the random code with high probability, that would be universal. Because there's only essentially a finite, so we're talking about here binary memoryless symmetric channels. There's, you know, this forms a compact set, so there's essentially only a finite number of those. Okay, for each of them, it's easy to show by the standard bounds that it is. Since there's only essentially a finite number, a union bound will show you also that you know, there will be codes that achieve it for all of them at the same time. Okay, and so not just there are, but with high probability, a code will be universal. Okay. Now, of course, if you have deviations and you deviate here, and that's maybe the critical one for the BSC, then that might no longer be the case. Okay, so then we have seen later on, we've seen yesterday and the day before spatially coupled, so iterative basically with a particular form, right? And so these are still random. And a very nice open question there is how much randomness you need. Okay, it's not something that I looked at. The constructions we had a lot of randomness in there, but there are constructions that have much less randomness in there. And in particular, if you can bring it down to something very small, then you can de-randomize them in polynomial time, but it's not something I talked about. They are universal, and they're efficient. Okay, and so maybe one extra thing that I can also add here is that they have optimum scaling, and it's something I'll talk about tomorrow, so I won't say much here. But optimum scaling, I mean that the error probability, if I think of it as a function of the length, that goes down as quickly. So I'm looking at a particular error probability, okay? And I'm looking as a function of the length. So I have maybe my threshold or capacity. And now I'm looking at, this is the error probability, this is the channel somehow. And I'm looking at how this behaves as a function of the block length. And I'm looking at a cut here, and I'm looking how quickly this goes to the threshold. And so I mentioned this a little bit yesterday, and I'll talk about more tomorrow. Then these codes have optimum scaling, okay? So the relationship between this delta here, the delta gap to capacity, and the n is such that the n scales like 1 over delta squared. Okay, and that's as quick as you can, as small block length as you can have. Here we said, you know, this is here, the delta scales roughly, the n scales roughly like 1 over delta to the 4th power. It's not exactly the 4th power, it's some power that depends on the channel, but order of magnitude. Here this scales roughly like n to the 1 over delta 3rd. And so these are, as far as I know, the only 3 kind of general methods. So if you want to prove that a code is capacity achieving, these are the only ways that I know where people have proved that a code can achieve capacity. Okay, so you somehow attach it to one of those. So the topic I want to do in the next lectures will be capacity versus capacity via symmetry. And so this will be an entirely different way to show that's capacity. And it will simply say that if a code is sufficiently symmetric, then that also guarantees that it achieves capacity. Okay, so will be, I guess each of these cases or each of these techniques are completely orthogonal to each other, and that, I don't really see any obvious connection. Okay, so this is basically what I want to talk about. Okay, so this is one motivation. There's a second motivation, and the second motivation is much more becomes much more practical, but I already mentioned it now briefly now. And that has to do that, good, so let's assume we have now all these ways of achieving capacity, and we still want to keep our research jobs, okay, and still want to be useful, okay, then what should we do? Well, the obvious thing is that these are all asymptotic things, right? These are things n go to infinity, but that's not what we're actually using. It's, of course, the first order thing that you're interested in. But what you're really interested in is, of course, the finite length performance. And this is not just of theoretical interest. The whole world now moves to whatever, real-time applications, real-time control systems, things where you might have devices that have extremely little power, like any application, Internet of Things, where you maybe have just little sensors, and it's no longer true the model where you're trying to transmit the continuous stream of information as efficiently as possible, but you just have maybe a few bits here and there to submit, so you automatically are interested in short block lengths, because you don't want to wait until 10,000 bits have accumulated, because this might be the next year you're waiting, right? You just, as soon as you have 20 bits, you want to send them. That's it, okay? And so if you're looking now at the finite length performance, then, as I mentioned, this has to do with this trade-off from the delta. None of the schemes that we know right now that are efficient are really, good in that sense, right? Because the delta, the relationship between n and delta, what we really would like is n is 1 over delta squared, and we know, even depending on the channel, we know exactly what the constant here is. So the constant here depends on the channel, and these are well known. So these are the finite length bounds that go back to Strassen in the 70s, and then Polyansky and Verdoux came up with an even more general formulation for these. And so we know all these constants and everything. So what we really look like is codes that scale as well as possible. And so the codes we currently know are not, the ones that we just talked about, are not really ideal for these scenarios. And so that's the motivation to go back to classical codes. So if you look back to classical codes, and in particular classical codes like Reed-Muller, or even better would be something like BCH codes. Now, so these are codes that if you empirically just run them for very short lengths, they perform even much better. And so, why, and we said initially people have even used them for space exploration and so on. So why have they slightly fallen out of favor? Well, there are several reasons. The first is we don't, historically, we don't even know how well they do, okay? So the first question, and that's what we're gonna talk about in the next few lectures, is, how good are they actually? Do they achieve capacity? That's the first order information. Then the second one you would like to know is the scaling, and I'll also talk a little bit about it, okay? So how is their scaling behavior, right? And then, of course, the third question is, and unfortunately, or maybe fortunately, we don't know, okay, is the question of efficient encoding. So the belief is, encoding and decoding, the belief is, if we can work through this program and find actually algorithms that are efficient for these kind of codes, then those would be the obvious choice to use for applications like in something like a 5G system. And so this is, perhaps the nicest and biggest open problem. And so in the past, people were just able to decode these things using algebraic methods. But these algebraic methods just do what's called minimum distance decoding, and typically they can't deal with soft information. So if you use, let's say, a Gaussian channel, and so you could first just maybe do hard decision decoding and then go back, but there's a significant loss that's incurred by this, so that's not really something that would be competitive with any kind of coding system. And so why do we hope or believe that perhaps we can do something now? Well, at least, I'll get back to it later on, at least when you talk about Reed-Muller codes, these are very, very strongly connected to polar codes. And so the hope is that somehow leveraging the ideas or the, things like successive and list decoding of polar codes, that you somehow can use that to actually decode now these very closely related Reed-Muller codes. So at least it's worth a fresh look, whether or not perhaps now with that in mind or with these techniques known, that we can go back. Okay, so this is perhaps the biggest and I think most interesting open question. I think if you can make a real, if you can find something, an efficient algorithm there, I think it's almost guaranteed that someone would use that, okay? If you can find it for something like BCH codes, these seem to be perhaps even better, but I don't here see the connection to polar codes and so on, so it's still worth looking at it, but perhaps we don't have any new tools. Okay, so this is the motivation. And the outline will be as follows. I first do a small detour. So remember that what we said is that what we really need for codes to be capacity achieving is that they have a sharp threshold. Right, so that they are useless above something and perfect below something. And so we'll go this route. And so the first thing we'll do is we'll look at a result by Seymour and Tillich, which is a really, really beautiful result, which gives you a sharp threshold result, which is kind of very universal, needs almost, basically no real requirements. It's a very, very general result and shows that as long as a code has reasonable minimum distance, its performance will jump like this, okay? And Seymour, Gilles Seymour, okay? Now, okay, so this seems to, from what I said, essentially prove already everything. Why doesn't then every code achieve capacity? There's a small hitch, okay? The small hitch is that what will jump is the block error performance, okay? So you will be either below it if the channel is good enough, the block error probability under optimum decoding, you will have 0 error probability, and above you will have probability of error 1. But the thing that I always talked about the jump was this exit thing, which has to do with the bit error probability, okay? And even though this seems like trivial, the two, but unfortunately this relationship is much more complicated. And so, it doesn't mean that just because if a code jumps the block error probability that the bit error probability jumps, okay? And so that causes a lot of problem. But it will show already the technique and the kind of ideas, and it's in general a really, really beautiful paper from 2000. It's another paper that I think Gilles was visiting me around 2003 or something, and he showed me this, and again, I didn't understand at all how beautiful it is until somehow later on it clicked, okay? And so I don't know why this paper hasn't really gotten more attention, but it really deserves. Okay, so then we'll see, this might take maybe the first hour, maybe it takes a little bit more. Then I'll tell you about a story, Reed-Muller codes and the binary erasure channel, and show that using the ideas will be similar but slightly different, and that's where symmetry will come in. So here we don't need any symmetry, but if we have a code that's symmetric, then indeed it achieves capacity, and I'll just show it to you for the BEC. Then when we go on, maybe tomorrow, depending, we'll see. Maybe I'll tell you a little bit about still a sharpening, so there's some stronger results have to do with better scaling, like nearly optimum scaling. So this result only shows that we achieve capacity. Something more recent, we show that this has a nearly optimum scaling in some sense. And then maybe in the last thing, I'll tell you about why originally when we discovered this, and there's a whole group, and I mentioned the people, we were very hopeful that this would be trivial to extend to general channels. And we were very, I think we said we were cautiously optimistic. Now we are just cautious, okay? The optimism has somehow vanished. It's very close, okay? So, we have thought about it a lot, but perhaps I think that's another very nice open problem because it connects to very beautiful theorems in computer science. And so if someone could find that, I think it would be very, very nice. Okay, so I'll tell you why maybe the generalization is not completely trivial, okay? And then that also will connect, essentially tell you what are nice open problems to solve in there. Okay, so that's the general outline. So let's get started. So we start with we start by the paper by Tillich and Seymour. So this concerns any binary, so consider any binary linear code. And it will have some length. Let's also take the rate, I'm not even sure we need it, and minimum distance. D. Okay, so the minimum distance, a linear code for, all the code words have this, if you look around, they see the same neighborhood, right? Because there's just some group action that's going on in here. And so if you look at the one that's closest, and the closest one, we have some distance D, which is somewhere a number between, 0 and n over 2. Okay, so you have this code. And so now you look at transmission over, right now in that paper, they just looked at either the BEC or the BSC. You can do this also over other channels. It turns out, and I'll state this maybe tomorrow, if you can prove that a code achieves capacity over the binary symmetric channel, and the error probability goes down at least like 1 over n as a function of the error probability. So you have, let's say, a sequence of codes where the error probability goes down at least 1 over n. And that's essentially any time a code achieves it, that will happen. Then you have actually shown that the code is universally capacity achieving, okay? So the BSC, so there are several notions of orderings of channels, okay? The simplest one is what's called degradation. But there's also more capable and more noisy channels. So these are orderings. And so this ordering is enough to show that if you can prove that it achieves capacity for this, it achieves capacity for everything. And so, essentially that's not much a limitation that we're just looking at things like that. Okay, so now what this result says is the following. So if I'm looking at a code like this, and so I have the following. So let's assume the code behaves something like this. This is the block error probability. So I'm sending a code word, I'm decoding optimally, and I'm recording whether or not the whole code word is the original one or not. And this is the channel here. And again, think right now just for the BEC. It's just easier to parameterize. But otherwise, think of this as, again, as the entropy of the BSC. So now do the following. Fix a delta, anything, and look at the 2 points here. So this is a function of n2. So think of epsilon is a function of n and of delta. So this means, what is this? This quantity is such that the error probability for the block error probability, when I take the parameter this, is exactly delta. Okay, it's just a parameter where the error probability hits either delta, and then if I do the same thing for epsilon n1 minus delta, it's where it hits 1 minus delta. Okay, it's just a point. I'm just inverting this curve. It's just a point where it achieves a certain error probability. And so since we're interested in a fast transition, and we're thinking of delta to be small, then what's important is, what does it mean fast? We're looking at how small this distance here is. Okay, so what we're looking at is we're looking at epsilon of n, 1 minus delta, minus epsilon of n and delta, right? And we want to know how large this is. Okay, and so what they prove is that there's some constant, and this is well known, I'm just not writing it down, over square root of d. Okay, or actually prove an inequality. So meaning the width, okay, so this is epsilon n delta. This is epsilon n 1 minus delta here. And what we're interested in is in this width, right? We say if the transition is fast, if this thing here is small, right? And so what we're always thinking is of we're thinking of always sequences. We're thinking of codes that where n goes to infinity, and then as long as, so this means if I'm thinking now of a whole sequence of codes, right, where that have some distance n and some distance maybe whatever I and here, right? And so as ni goes to infinity, the di also goes to infinity, right? As long as the distance of the codes goes to infinity, then it means that this thing here will go to 0, right? So eventually, this means we'll get a jump. And if this is true for any delta, this means we get a, essentially we get a jump function like this. So, now this, so now this has to do exactly with the scaling, right? So how fast can this go? And so that's a very good question. So let's just check. Is this result good or not? Well, we know that the best codes, right? So we know that for the best codes, the distance can be some alpha times n, right? So it cannot be better than that, but it can be as good like that. So let's just check what this would say, right? This would say that this transition, right? So this transition width, this would say that this transition width here, delta, okay, behaves like 1 over square root of n, right? Because now, forget about the alpha, these are just constants here, right? Or in the other way, that n would be 1 over delta squared. Okay, and constants, I'm omitting constants here. Is that clear? And remember that I said that this is the best behavior you can have. You cannot have any better scaling. So the result is actually very strong, right? In a sense that up to the constants that are involved in here, there are alphas and some other constants in there, but these constants are not crazy constants. These are not 10 to the trillion to the whatever, It's not the standard computer science result where, e to the e, whatever, okay? So these are very reasonable constants. And so up to these constants here, this gives you optimum scaling, okay? And so even though this is just a bound, this is very, very strong. And so for example, for code, something like for a Reed-Miller code, the distance is not optimum. So the distance is only square root of n. So this gives you the fourth power here, but this is just a bound, okay? This doesn't say that the scaling is like that. This is just the result that you get from this one here just gives you that bound, okay? We believe that actually the scaling is better than that, okay? It doesn't say that minimum distance is linear minimum distance is necessary for optimum scaling. It just says that, that it's sufficient for optimum scaling. Fine, okay? So, what I want to go through now is a little bit show you where this result comes from. And are there any questions about the basic thing itself, what I want to show? So now, how does this differ now from what I said previously? This is the block error threshold, okay? This does not mean that a sequence of these codes achieves capacity, right? Otherwise, every code that has a sequence of codes that had distance going to infinity would achieve capacity. That's not true. It could be very well that this is like this, but that the bit error, is already, the bit error probably could be, there's unfortunately a factor n that you have between the block and the bit error probably, and it could start already, somewhere. Of course, once you have block errors, you also have some bit errors, but let's assume you have very small minimum distance, right, then the bit error probably could be still 1 over whatever, square root of n or something like that, right? So it could be essentially 0. And the bit error probably could only just start there. And so this would mean that such a code doesn't achieve capacity. Good. So let's see how we can, how this is proved. And so okay, so let's think of just the Hamming cube. Okay, so we right now forget about coding for a second. And so this is one instance of this very nice machinery that comes from computer science. So let's just take the Hamming cube. Now, since it's difficult to draw a Hamming cube, I'll just draw a box, and I'll think of just points in this box, okay? Because what I want to show is, want to show certain monotonicity. You can think of it as in the two-dimensional real plane much easier, but it would be hard to draw this in the Hamming cube. Okay, so you have this, and let's take a subset omega, right? Now, what I want to do is, I'm going to look at subsets that are monotone. So what this means, if I'm drawing this in R2, and again, this is the Hamming cube, but you will get the idea, is that if this was in R2, then this set would be monotone, right? So what does it mean that it's monotone? Okay, it means that if omega is an element in this, okay, and omega prime is, so let's say, and d of omega and omega prime is, let's say, 1. So let's say there's another one that is distance 1 away, okay, and the omega is larger, the omega prime is larger than the omega in the standard partial order. So what is the standard partial order? Well, if I have, let's say, this word here, right, so if I have just a 0 and 1, then 0 is smaller than 1. That's the order component-wise. And I extend this to a partial order over the components, where simply, for example, this vector here, right, would be larger than this, because it's at every component, this has a 1, this has a 1. But you know, there's also potentially a 1 here where it's a 0. Clear? Okay, so actually I don't even need that. For this, I don't even need this condition. So let's just say that and omega okay, so in pictures, if you think about pictures here, this is simply something like an upper triangular thing that doesn't have any holes in there, right? So if you had this, but you had, let's say, that this was included, then this wouldn't be monotone, right? Because if you went from here up, then this would no longer be included. Is that clear? Everyone is clear what I mean with monotone? Yes? Okay, good. So, okay, so you have this, and it's a monotone set. And so then there is a very nice relationship here, which is called Rousseau's inequality, or Rousseau's, no, actually Rousseau's equality, I guess. And so we need one more notion. So what is a very natural probability distribution, right? So we can just take the Bernoulli product measure. So it means, let's just take with parameter epsilon. And so then the probability or the measure that I assign to some omega is then what? It's just, you know, it's just this. It's just the epsilon to the number of ones. So I'll just do it like this. Okay, that's the number of ones that I have in the omega, right? Times 1 minus epsilon, the number of n minus the number of ones, right? It's just what's the probability? I give you a sequence. You just flip a sequence with probably epsilon, it will be 1. Probably 1 minus epsilon, you pick a 0. And then what's the probability? I give you now a 0, 1, 1, 1, and so on. What's the probability that you get that sequence? That's it. Okay? So now, of course, you can extend that to the measure of any set, right? And so that will just be then the sum over all omega in that set of mu of this, right? So it's just the probability of this set. And so now this Russo thing says now the following. It says that, so now the question is the following. If you have this, okay, and you have an omega, let's assume the omega is not, the trivial one, let's say either the all set or nothing. So, okay, so you have a certain measure, right? And so now the question is, how does this measure change when you're changing, let's say increasing a little bit the epsilon parameter? So what I'm looking at is, okay, so I have this measure, and I'm just a little bit, let's say, increasing the epsilon parameter here, right? Now, what should happen, right? Sorry? The mass will go upwards, and that's exactly, so perfect, that's exactly what I want to now show. And so you can write this down as follows. So this is equal to, and so we'll just do this now in a second. So this will be just a second. And this will be, and so here we're having over all omega. So this says the following, that this derivative, okay, there's just a 1 over epsilon in front, is the following. So I need to tell you what this is. You go over all the elements, all the omegas, okay, and you do the following. So h of omega is the following. If it's 0, if omega is not, and I'll tell you what this means, is not in the boundary, and it's equal to the number of neighbors in omega phi if omega is in the boundary. Okay, so this will take a second now to explain. So what this is the following. It's some multiplicativity. There's the notion of the boundary of the omega. So here it's quite easy to see. So these are points that are in omega, but have the property that there exists at least one element that has distance 1, and this is not in omega. Okay, so this is omega c, and a point on the boundary is a point that is in omega but has a neighbor, at least one neighbor, that is in omega c. Make sense? And so in general, a point here could have several neighbors, and the number of neighbors it has, the neighbors here all means a distance 1, that's this h. Okay, that's the h. But if I take the omega to be either here, which is outside, or here, but in the interior of the set, then this is 0. Okay? So that's the notion. And so the claim is that the derivative is exactly equal to this, and you already said why, okay? But I just still want to go over this argument here. Okay, so why is that true? Okay? This part is actually very, is very easy to see, so that's why it's worth going over it if you haven't seen it. So just take these points and make like a lattice representation. Okay, so it means we're looking at the partial order, and we're looking at the lattice that corresponds to the partial order, right? So we have 0, 0, and then there are n neighbors here, from 1, 0, 0, 0, whatever, up to 0, 0, 0, 1, and then, we have 1, 1, 0, 0, 0, whatever, okay? And then to 0, 0, 0, 1, 1, and so I think, right, it's kind of clear, 0, 1, 1, 1, 1, up to, right? And so we have all this lattice representation that I'm thinking of. Clear? So now take any point here, and let's assume, so this is the, this has weight, this one has weight 0, this one has weight 1, so these are shells of particular weight, and let's assume that the weight of this is, let's say, let's maybe not make it W, let's make it K. Okay, so I'm taking a point here that has K ones in there, and the rest is 0. So what is its measure? Well, it's mu epsilon of this point. Let's call it omega here, right? Is, okay, epsilon, as we said, to the, I know that this has weight k, times 1 minus epsilon to the n minus k, right? And so now what happens if I take the derivative? Right, so how does this change when I take the derivative, when I a little bit turn the epsilon? Well, we have two terms, right? We take first this one. So we're having k times epsilon to the k minus 1 times 1 minus epsilon to the n minus k, right? That's the first term. And if I take the second term, there will be a minus coming from the interior here. So we have minus n minus k of epsilon to the k times 1 minus epsilon to the n minus k minus 1, right? So these are the two terms. I mean, I haven't done anything. But now there's a very easy interpretation of what that means, right? So if this one here has, let me just draw it generically, has k ones, and then n minus k zeros here, right? So what does the first term correspond to? How can I think of the first term? Sorry? So this is mass, and where does, so this is mass that comes in, okay? So I can think of a flow, and where does this mass come in? Well, it has exactly k neighbors here, right? And the k neighbors come from these, you know, taking away any of these guys here, right? So I can write this as k, so the way I could write it is as k over epsilon, and, oh, sorry, they have actually minus 1, that's actually correct, and I guess I need here, and let me just see, I want to write it like this, k minus 1, and I want to have here, I just want to take out an epsilon, just a second. No, okay, let me write it like this. Okay, so I write this like this. So I just took an epsilon out, and this is again the measure of the point itself, right? So it means I have a certain weight that comes in from these k neighbors in here, and this corresponds to these terms. And then I have here n minus k that corresponds to the other terms, where I'm taking weight from these guys, right, and distributing weight further up. Is that clear? Okay. So now, if I'm thinking of this, then this picture, you know, why this formula is pretty clear, right? So what do I have? I have this point here, which I can just think of this point here, right? So let's assume that point is here, and it has some neighbors up and it has some neighbors down, right? Well, it's completely irrelevant that the flow of the epsilon, or the flow of the weight goes in here, right? Because both this point and also, you know, the points here, right, they're all still outside. This doesn't change anything. Clear? If I have a point inside here, also it doesn't make any difference. This weight was already in there. It's just associated now to a different point, right? But if I have a point here, that's exactly where weight flows, you know, the first time from the outside into this thing, okay? And this corresponds exactly to this k, the first term here, right? And so I have a 1 over epsilon out here. And so now the only thing is that in general, not all the k neighbors will be outside, okay? But I should only count those neighbors that are indeed outside, and that's exactly the h that I have here, okay? Yes? Yeah, but I don't just want to say that the math moves up. I want to say that this is the exact formulation. This is not just, you know, I'm not just saying it increases. I'm saying exactly how it increases, okay? So you're right. If I just wanted to say, you know, why is it an increasing function? You're absolutely right. But I want to say exactly how it increases, okay? Make sense? Good. Okay, so this means all we have to know is if I know this set, and I can tell you at the boundary what this number here is, okay, then I can actually tell you how fast things increase, okay? So now we are almost done trying to use this for coding. So we still need to know a little bit something. So this right-hand side has something to do with, I integrate over everything, but h is 0 in the interior, right? So this is some number here. But essentially, the size of the boundary set in relation to the size of the set, how do I know how big the boundary is? Perhaps the boundary is very small, right? And remember, what do I want to do? I want to show, so this is the derivative here, right? I want to show that this derivative is large. If I can show that the derivative is large, then it means that the function must jump very quickly, right? So I want to show that this thing is large. Well, one thing is to show that this is large, hopefully, okay? But I also want to show that the number of points that are on the boundary, that's also not too small, okay? Otherwise, I'm sunk. And so the initial, and there are many improvements, and in Seymour's paper, there are also things, but the initial inequality by Talleyrand gives you some relationship between what's happening at the boundary and what's happening in the thing. And so this is not a trivial inequality. So he proved an inequality by induction of the following form. And the exact formulation here is not so important. I just write it down for completeness. Okay, so he proved an inequality that says something about, so this is almost the same quantity, but now I have a square root in here, okay? And so he proved an inequality that, so the nice thing is that now that on the right-hand side, we have again the measure of the whole set in there, and not the measure of the boundary in there, okay? And so doing this and then just Cauchy-Schwarz inequality, you get the following inequality. So the rest is now just routine, and you get, first let me write everything down, and then I'll tell you what these things are. Okay, so now we have, so now this is just an inequality because we have used here the inequality. And so now we have our equation that we're after. And if you forget about all these things, which are just some constants, then this says that the derivative here of the set, okay, so now we have a quantitative thing, how fast this has to go up, right? So as soon as this set is not completely trivial, okay, some delta, then you see that this will be also of order delta here, okay? And so the only thing I haven't explained is what this epsilon, what the delta here is, this delta. So this delta is unfortunate, I shouldn't have used delta. Delta is the minimum of all these h's that are non-zero. Okay, so it's the smallest multiplicity that have the boundary. So this means the following: if you can prove that everywhere on the boundary you have some reasonable multiplicity, right? So something that grows with n, then the derivative here, right, you have a differential equation, the derivative here will give you something, a derivative that as soon as you're non-zero, or you're bounded away from 0 and 1, the derivative will be growing with n to infinity, right? And for example, in this formulation could grow as fast as the square root of n, right, if the delta was of order n, right? And so this means that now, when you solve this equation, you will exactly get that things go up, okay? And this derivative here will be exactly what you're seeing here, okay? And so, so from this formulation, what we get is that there's a fast transition, right, between if you're using that. And so that's a very generic result. And so Seymour and Tillich, first of all, improved these inequalities. They have an even much nicer, but a slightly more, so a stronger, but a slightly more complicated expression. That's why I didn't write it down. But in particular, they realized that you can apply this very nicely to coding. Okay, so let me now tell you how this applies to coding. This is completely generic. No, this is, you have to take, you know, the original thing, you have something originally from h omega times the mu. You write this down as twice the square root of this. You once see that you divide by, you divide this by 1 over the minimum you have here, or the square root, sorry. You put this in here, then you have here the h by the delta. This will give you 1, and now you apply Cauchy-Schwarz to this, okay? Good, so now let's just see how this applies to coding, at least when we're looking at block error probability. So I think before the break we can still do the BEC, and then perhaps we still do the BSC afterwards. So for the BC, okay, the claim is that this delta is equal to the Hamming distance, okay? And for the BSC, the claim is that the delta is equal to the Hamming distance over 2, okay? Now, the 2, of course, is significant, but nevertheless, the scaling is the same, right? So this means that, for example, if you had a code that has minimum distance here, this transition width would be of 1 over square root of n, okay? So that's very good. Good, so let's just check maybe for this why this is true. So what is exactly the setting? So for both of these channels, due to symmetry, you don't actually need to look at the combination of the code word and the error. The error is, you know, when you do the decoding, it doesn't matter which code word you send. Whether you can decode or not only depends on either the set of erasures or the set of errors. Okay, so you can assume, that's what's called typically the all zero code word assumption. So you can assume that we send the all zero code word. And so, of course, we don't tell the receiver that, but we send the all zero code word. Now we send 0. Now this goes for the channel, okay? And so what we will see is something maybe perhaps of whatever, 0, 0, question mark, 0, question mark, something like this, okay? And now, of course, the all zero code word is compatible with this, but there might be some other code word that's compatible with this. And we can decode if we will not be able to decode, okay, block decoding, exactly if there's a code word that is covered by this noise, okay? So if there's a code word that, for example, looks like this, where we have here the question marks, all the 1 symbols are covered by the question marks, right? Then the decoder will not be able to tell whether it was this code word or that code word here, right? They're both equally likely, okay? They're both possible, and hence it will declare a decoding error. Okay, so that's exactly when it cannot decode. So what will be now my natural set omega, okay? So my natural set omega is the set of erasure patterns that are, so let's see, do I want, that give error. Okay, so I take my set of erasure patterns that give errors, and so what is the mapping? Here I wrote 0 and question mark, okay, because code words is 0 and 1, but before I took for the omega 0 and 1, okay? So I'm just simply replacing a question mark with a 1, 2 here. Is that clear? Okay, so then this omega will simply be, as beforehand, will be something like this, okay? And so this would, some point like this will be something like this. Okay, and whenever I see a 1, that means that this position was erased. Okay? Now, it's clear that this is monotone, right? Because not being able to decode means there's a code word contained. If I'm adding an extra 1 to it, then the same code word is still contained, and hence, clearly, this is monotone, right? So this is clearly monotone. It's also clear what this means, right? So what is this quantity? right? So this is exactly my probability of error. So that's exactly what I'm interested in. And so I'm exactly interested in how quickly this probability of error jumps from 0 to 1, right? And according to this, what it says is that it jumps here exactly 0 to 1, and this is of order 1 over square root of, so it's this delta here, 1 over square root of dh, okay? And we still have another function. Do I want me to write? I guess it doesn't matter now. Okay, so we can still write down the behavior. So there should be a log of 1 over this delta here, this small delta. Okay, so you know the scaling right now. This is the scaling for fixed delta, but if I also want it as a function of the delta, this should behave like this. Good. So now. Okay, so the only thing is I still need to prove that indeed this is dh, right? This is just. Sorry? This small delta? This is basically the transition from where, so this goes from delta to 1 minus delta, okay? So because I can let that delta also go to 0, right? And I want to know how this behaves there. If it's a constant, it doesn't matter, but if I think of it as something that I want to also let go as a function of n, then this matters. Okay, so now I still need to tell you why this actually, you know, why is it true that, that I have this delta here. So let's consider a point here, okay? So I have an erasure pattern somewhere. And so let me just draw the erasure pattern where I have, without loss of generality, have all the erasures in the beginning, just so that it's easier to draw, okay? Good, so, okay, so I have the erasure patterns here, okay? And this thing here contains a word, okay? So contains, for example, this word here. This is, let's say, a code word. So this is the erasure pattern. And this is a code word that certifies that this erasure pattern is, so this is erasure pattern omega, and this code word here, C, that certifies that via C that this omega is in the set of things that I can't decode, right? Because it's covered, right? But let's assume now that this is not just in omega, but that this is actually in the boundary, right? So if it is in the boundary, this means that there must be one position that if I take one position and I uncover now this position, right? So if this position I flip now from 1 to 0, right, that it no longer contains a word that's covered, okay? So the claim is that points on the boundary have only a single code word that's covered, okay? So let's postpone the proof of this. So the claim is that if omega is in the boundary, then there's only a single code word that's covered, other than the 0 code word. If that's true, then the result is obvious, right? Why? Because every code word, non-zero code word, has at least, dh. This number here must be bigger than the minimum distance, right? The minimum weight is equal to the minimum distance, and we would be done, right? So the question is just, why can it only have a single one? Well, let's assume there was a second one, okay? Maybe, okay, let me just finish this. So why is this true? Because if then I have these ones, then I can, of course, flip in each of these positions, and then this will give me down, okay? But let's assume I had a second one, maybe this, okay? Okay, if there was a second one, right, then of course the XOR is also covered. Okay, so if I take a code word that's covered, another code word that's covered, the XOR is also covered. Clear? So I have a code word, and I have C plus C prime, so 0, 1, 1, 0, 0, that's also covered. Right, so I have not, as long as I have more than one, I have at least 3 code words that are covered. But now look at the following. In no position will all 3 code words be 1. Is that clear? Because they're the XOR, right? If 2 of them are 1 at some position, then the third one will be 0. And so this means no matter which of these bits I flip, okay, there will always be one code word which at that position stays 0, right? It will still be covered, or it still keep covered by the erasure, and hence this is not actually a boundary point. Okay, logic is, this is only a boundary point if I can find a position when I flip this position and uncover it, there are no longer any code words that are covered, right? If there are at least 2 code words in there, then there are at least 3 actually in there, since it's a linear code. And at any position here, or okay, at no position here, will all 3 code words be 1. So no matter which of these positions I uncover, there will be always 1 remaining. So for example, if I look at this position, this is 1 and this is 1, so these will be killed. Okay, they are no longer covered. But this one is still covered, right? If I do this one, this will no longer be covered, but this is covered, right? And so on. So there's no position that I can find when flipping it. All the code words will be gone, the covered ones, right? So hence, it's not a boundary point. Fine? So we're 1 minute late, okay? I'm so sorry, okay. So we'll take a break, and when we come back, maybe I still give you the proof for the BSc, and then we'll do the actual, this is only the block thing, and we go to the bit that brings us to capacity achieving.